Hello, welcome back to Differential Geometry. This is episode 5. Just before we begin, I want to recommend everybody turn up the speed of the video because I talk really slow, so turn the video speed. I recommend 1.5 times. That's what I watch my own videos at because I talk really slow. So yeah, just wanted to give you that little tip. Okay, so today we're going to be talking about more topology. And, well, let me remind you of what a topology is. So let M be a set, and a topology, so tau is a topology on M if, well, it needs to have the following three properties. So it needs to have the empty set and the whole space, so that the whole space is open and the empty set is open. Second of all, tau needs to be closed under unions. So if A and B are in the topology, then A union B is an element of the topology. And third of all, tau must be closed under finite intersections. Great, so these are the three axioms of a topology. And well, we know some topology examples already. We know that the topology on R2, for example, is open sets in the plane, where if we have an element of the open set, you can always draw a ball around that element which is contained within the open set. So I'm going to make this a little bit easier to work with, and I'm going to show you how you can generate an entire topology from only specific open sets. So for R2 we've got a lot of open sets that are ugly. They have curved edges and stuff. But we know open balls are nice, so can we generate all open sets from open balls? So the way we do this is using a base. So a base for tau. So it's a subset of tau. And so these are specific open sets that have some nice properties. So for it to be a base, we need to have the following two properties. We need the union over all the basic elements has got to be equal to M. So if we took, for example, the plane and we unioned all the balls together, you would get the plane back because it would just be shading in the entire plane. And second of all, so this one is going to be a little bit more complicated. So let's say B1 and B2 are basic open sets, then for all x in their intersection, we have the following property. So there exists some B3 in the basic or the base of the topology, such that x is in B3 and B3 is completely contained within the intersection B1 intersect B2. So this is saying that if we have two open sets and you take their intersection and you put an element in there, then there's got to be some third basic open set in that intersection. So what this does is it allows us to generate all open sets, and there's a proof of this theorem that it generates all the open sets, but I'm not going to do the proof. So in general, if U is an open set, then there exists some collection of open sets in the base such that the union of all these open sets in the base is equal to U. So this means that if I draw some arbitrary open set, then I can always pick basic open sets that union together to form the larger one. So this is quite useful because we already know an example of a nice base. A nice base would be something like the open balls. So example, Rn with the regular old metric space topology. This has a base given by the set of all open balls. Great, so that covers bases, and next I'm going to cover separation. So let me define separation for you. So let x and y be elements of some topological space. Then x and y are said to be separated if there exists some open set ux such that x is an element of this open set and y is not an element of it. And similarly, there exists a uy such that y is in uy and x is not. So this is saying that if you have 2 points x and y, then you can surround them in neighborhoods which do not intersect. Or weakly, you can surround them in neighborhoods which are not neighborhoods of either point. So x has a neighborhood which is not a neighborhood of y, and y is in a neighborhood which is not a neighborhood of x. So that's what separated means. And another important notion is that of distinguishability. So if for all, so let's say I pick a point x and y. So x and y are elements of M. So let's say that they have the exact same neighborhood. So let U be a neighborhood of x if U is always a neighborhood of y, then x and y are said to be topologically indistinguishable. So this is why, or this is because if you took two different points and they always had the same neighborhood, so there were only ever neighborhoods that contained them both, this basically means that you could never separate the 2 points. They're indistinguishable from each other. So you can't use topology to study the differences between those 2 points. You can only use other kinds of mathematics. So this is an important notion. And it leads us to a few different classes of topological spaces. And these are really important to keep in mind because depending on what class your topological space is, you're going to get different properties and you're going to be able to do different things on the space. So these are called the separation axioms. And they describe when 2 points on a space are separated from one another. So the first one is called the T0 axiom, and there's a T1 axiom and a T2 axiom and so on. So T0 axiom says that if for all x and y in M, x and y are distinguishable then the space is said to be T0. So this is called also a Kolmogorov space. Kolmogorov was a big mathematician in the 20th century. You're going to hear his name quite a bit. So T1 then is called a Frechet space, and it says that two topologically distinguishable points are separable. So this makes sense. It makes sense that if you could distinguish the 2 points, you could come up with 2 neighborhoods that separate the points. Also, of course, it needs to be T0 in order to be T1. So in order to get from T0 to T1, you need the points to be separated, not just distinguishable. So that doesn't always happen. There are counterexamples to all of these things. So this is called a Frechet space. Yeah. And the next axiom is called the T2 axiom, and this one's probably the most important. So this says that any 2 points, so any 2 points are separable by open sets. Right, so if we defined up here separability with respect to neighborhoods, these didn't have to be open. In fact, they could just be different sets. So here we require that the sets are open that distinguish the points. And this is called a Hausdorff space. So Hausdorff spaces have very nice properties. You can take 2 points, x and y, and you can put open sets around x and y that are completely separated. There are more axioms. There's T3 and T3.5 and T4 and so on, but we're not going to talk about those today. All we really need for now is Hausdorff. So after defining Hausdorff, I think it's important to go on to some new content, because now we've seen a whole lot of different types of topological spaces. We've seen a couple structures on topological spaces, such as a base, but we haven't done very much with them. So next up, we'll talk about continuity. Okay, so let me define continuity for you. Suppose you have a map F from one topological space M to another one. I'll call it N. What is this? Okay, and you want F to sort of have some notion of continuity. So let's look at Rn, for example. Rn has a notion of continuity where if xn goes to x as n goes to infinity, then F is continuous if f of xn goes to f of x. And this should apply to any sequence. So for all convergent, geez, my writing's so bad right now. Continuous if for all sequences xn, with limits, of course. So this is continuity on Rn. And we're going to take a look at continuity on a general topological space. So first I needed to find something called the preimage. So preimage, let U be a subset of n, then F inverse of U is defined to be the following set. It's all x in M such that F inverse of y equals x for some or actually for all y in U. Yeah, this is a bad definition. Let me rewrite this. It's all f inverse of y such that y is in U. There we go. So this is the definition of the preimage of U. Preimage of U. So we're going to need this. So a function f is continuous if for all open U in Y or N, f inverse of U is open. So this defines continuity on a topological space. And let me show you why this defines continuity. Okay, so let's start with the definition of continuity on Rn, and I'll show that that's equivalent to this definition, so Rn. So let f be a continuous map on Rn, then for all epsilon greater than 0, there exists some delta such that whenever x and y are within delta of each other, f of x and f of y are within epsilon of each other. So this means that for all epsilon balls centered around some point y, f inverse of this epsilon ball is the same as some delta ball around f inverse of y. So this is saying that the inverse of any epsilon ball is another epsilon ball, and this means that the inverse image of a topological basis set, so a basic open set, is a open set. And therefore, because a base generates all of the topology, this extends to the entire topology on Rn. And so this basically tells us how continuity works on general topological spaces. You can take continuity from Rn and show that it's equivalent to this definition. And so now we've got some definition that works for both general spaces and Rn. So another thing that continuity has that's a nice property is that it preserves Hausdorff spaces. So if M is Hausdorff and N is a topological space, and f from M to N is continuous, then f of M, which is defined to be the set of all elements in the image of f, so it's f of x such that f is in M, this is a subset of N. And this space, this subspace of N, is Hausdorff. And there's a few more properties that have to do with compactness, but we'll get there later. I think that's all I have for this video. Thanks for watching, and I'll see you next time.